So today on the channel we're going to talk about sorting, and specifically we're going to talk about abstraction and how, as a practicing software engineer, I had the wrong idea of what abstraction really meant. And it's not until I started studying TLA Plus that I really got to the heart of what abstraction means. And so I want to ask you a question, and I want you to think about it as we go through the specification for sorting, and we're going to do it in 2 steps. What is the opposite of abstraction? So we say we abstract things all the time in software engineering, but what is the reverse of abstracting something? So with that picture in your mind, what is the opposite of abstraction? And what does that actually mean? Like, what is the process by which we abstract things? And what is the reverse? I propose that the reverse is refinement. Abstraction means to remove detail, and refinement means to add detail. That's all it means. It's not adding layers, it's not putting on a better interface, it's not getting a better library or a different dependency. It's simply a matter of controlling how much detail you use. So this is what we're going to write today. We're going to take 2 specifications. We're going to do what is the essence of sorting? What is basic sorting? And we're going to call that sort by magic. The essence of sorting is that you start with something that is not sorted and you end with something that is sorted. That'll be the first specification that we'll write. The second specification will be bubble sort, and we'll just write a bubble sort implementation that achieves the same thing. Now, this is no different than what we would do in a bigger system. We have this very abstract kind of rough idea, what I'm proposing, a low detail idea, and then we're going to realize it, implement it, and it's going to have lots of real world kind of use cases and challenges, lots of detail in it, right? But what TLA lets you do is it lets you correlate these 2 specifications. It lets you state that everything that's true of one system, the abstract system, is also true in the refinement system. And that's called a refinement mapping, and you can show that one system implements another system. And so this is a very powerful technique. It's been called by some as the killer feature of TLA Plus, that you can write successfully more detailed models, and each of those models can be shown to correlate and implement the same temporal properties and invariants. So let's start at the beginning, and let's implement sorting. Okay, we are going to start the same place we always start, with our init, our next, and our spec. The hello world of TLA Plus. So we're going to have this variable a, and this variable a is going to have some kind of value in it. So what's in our picture? Our picture had 2, 3, 4, 5, 1, something like that. And we're going to sort a. Okay. So let's start with, we're going to have a variable, and it's going to be a, and we're going to initialize a to that sequence. Okay. Now we're going to say the next state of a. Remember, we're going to sort in one pass. We're just going to, it's going to be unsorted, and then it's going to sort. We're just going to say it got sorted by magic. We don't care how it worked. We're not applying bubble sort. We're not applying quick sort. We're not applying insertion sort. All of these are specific implementations of what I'm proposing is sort by magic. The essence is something is unsorted and then it is sorted. And that's the abstraction that we're building today. So we're going to take the init, then it goes for next, vars, weak fairness, vars over next. Okay, let's define what vars is. Vars is equal to a. And then we are just going to say sort by magic a. So we are in the first state A, sort by magic in the final state. Great. What does sort by magic mean? Sort by magic is going to take a sequence, and it is defined as choosing a permutation P that's in the set of permutation sequence of seek, such that it is sorted ascendingly. There is a permutation of all the permutations of the sequence. There is one sequence that is sorted ascending. Just choose that one. That's what we want. Okay. So what is the permutation seek of a sequence? It is simply defined as apply indices of a sequence of P such that P is in permutations of 1 to the length in sequence. Okay. We're going to need a few libraries for this. Extends TLC, integers, folds, sequences extended, and finite sets extended. Okay. Finally, we need apply indices of sequence of our indices and DICES. I is into 1 to the length of the sequence mapped to the sequence of the indices of I. Generate all of the permutations. Find the one that's sorted. That's the one we want. That's sort by magic. Again, remember in earlier videos, we need to, sometimes when we're writing specs, we need to drop the idea of, well, this is going to be inefficient. This isn't going to be computationally reasonable. TLC has a different approach for enumerating things, and you simply want to state what you're looking for mathematically and let the optimizations work itself out. And sometimes the specs do get really, really big, but this is where the small model hypothesis comes in. Because we're blowing out and looking at every single state of all permutations of the system, we can look at a smaller input set. And so we're not going to enumerate for 1 million elements. We're just going to enumerate for 5, but all permutations of that 5. Now, what is sorted ascending means? So is sorted ascending of a sequence is defined as all of the values A and B that are in the set of 1 to the size of the variable we're looking at, such that A is less than B for the sequence of A is less than or equal to the sequence So for all indices, A and B, the value at A is less than or equal to the value at B. And that is ascending. For descending, just for completeness, the sequence A is less than B, such that, can you take a guess? The sequence of A, the value at A, is greater than or equal to the sequence at B. And that's descending. So what is n? N is a constant. And it's going to be the size of our input set A. So for this, it will be 5. Okay. And let's assume that n is greater than 1. Doesn't make sense to sort an array that's of size 1, so n better be less than 1. All right. This is our specification. What properties do we want to show? Well, if something is sorted, if we have an algorithm that sorts values, then we should define what that means. It starts at some unsorted state. It might be sorted, but it's arbitrary. And it arrives at some sorted state. So eventually, we should be sorted ascendingly. And that's eventually, always, is sorted ascending of A. We have our type OK. It's okay. It's simple. Remember, this is our abstract system. We don't have a lot. The length of A is equal to n. We expect that in every state, the size of A is constant. It's not going to be changing. Let's run this. Create a new model. This is just going to be abstract model. Okay. As we said, this is going to be 5. We have our invariance. Our invariance is type OK. All right. And we have our property, add, eventually sorted ascending. All right, let's run this. And there it is, our model checked. But just for completeness, or just to like explore the model a little bit, kind of see what's what. Let's also say eventually we are descending. And let's try and tell our model that we should both at the same time be eventually sorted ascending and descending. This obviously should fail, but I spelled it wrong. But let's just see it. Sometimes watching things break can teach us a lot. Eventually, did I spell it wrong? Yes, I did. Copy, edit, finish. Okay. Temporal properties were violated. Okay, that makes sense. Which one? It was the descending one. This is an ascending value. So now if we changed this part to descending, now we are choosing a permutation that is descending. We should expect this sequence to change, right? Run it again. And of course, we get a descending sequence now. temporal properties were violated because we're trying to check both properties at the same time. And there we go. So that is a very simple specification that describes the essence of sorting. Sorting as you are unsorted, there's some magic step, and then you are sorted. And our entire state machine right here is defined in a single step, 1. But TLA Plus lets us do something that's a little bit more magical. Instead of just sorting a single sequence, it will let us sort all sequences. And it'll apply our specification to all sequences and verify that no matter the ordering, we will be able to show that we can go from unsorted to sorted for all of length n. So let's see what that looks like. We're going to make an init2. We're going to call it A. And we're just going to define it as from 1 to n. So now A is some sequence of values, set of values, from 1 to n that are some arbitrary selection of the natural numbers, nat. Okay. We're going to write spec2, or let's just change this to that. Okay. Now we're going to do something that's a little bit peculiar. We are going to, the natural numbers is an infinite set. TLC cannot enumerate an infinite set. So we're going to provide a finite set that we feel is representative of our system. So we're going to come into spec options, definition override, and we are going to override the natural numbers, where it's in this list somewhere. Yeah, there it is. We are going to override it to the sequence 1 to 10. 1 to 10. So now we have said the natural numbers that we care about for this system are all the numbers 1 to 10. And if we run this now, our system is quite a bit bigger. It is now running 100,000 permutations, 100,000 initial values to verify that our system can check for sortedness. There we go. So we've shown that starting from the initial states 2, so that's the one that has generate all of these permutations of the natural numbers, 1 to 10 that we defined, show that we can arrive at a descended sorted value in every case. And that is abstract sorting. So now this might feel like, well, how useful was that? Why was that interesting? Well, it was interesting that it let us express what sorted means, and it let us express what an algorithm that sorts stuff means. So now we have the essence of what sorting is, and we can go implement a specific algorithm and verify that, hey, does it always arrive at the same sortedness as the abstract? And we'll do that in the next video.